Hey there, ho there, hi there. It is time to talk about energy and chemical reactions. You've just watched two demos, one that was illustrating an exothermic reaction, the other illustrating endothermic. If you're in a classroom, you would see I'd write exothermic above the door, and on the outside of the door, from the hall side, I'd write endothermic. And there's a reason for it, apart from my insanity. So we have a capital H, and that refers to heat and also enthalpy. Delta, the Greek letter delta, means change. So delta H means a change in enthalpy. So what we do is we look at the energy the products have and we subtract the energy the reactants have. And that difference is going to tell us about whether we produced heat or absorbed heat. Exothermic reaction produces energy. That energy might be in the form of heat, it could be in electricity, but oftentimes it's heat, and that's why we have the H. If delta H is negative, it's exothermic. If it feels warm or hot, we do a reaction and you touch the surface or the outside, say, of a container and it's gotten warm, that is exothermic. The heat is trying to leave, it's trying to exit, it's trying to go to the surroundings, and that's why I write exothermic above the door, as the heat's trying to leave, just like you try to leave when you're sick of this class. Now, when we form chemical bonds, usually that is going to be an exothermic process. And so synthesis and combustion reactions tend to be exothermic. This is a crazy graph. Across this side, this would be like time going down here, progress of reaction. Here we have zinc and oxygen. That means we're going to burn zinc. In grade 12, we worry about this peak. That's just the threshold energy we need to have to make the reaction occur. So we're looking at potential energy. But the bottom line is when we finish off with the zinc oxide, it has less energy than the reactants. The products, less energy in reactants, that is exothermic. The delta H is pointing down. The arrow pointing down, that means it's negative, less than 0. If we're writing out as an equation, here are the reactants, here are the products, and the energy is on the product side. So to get clues about if something's exothermic, delta H should be negative. Energy should be on the product side of the equation. Now, this is the beauty of chemistry. If you know all that about exothermic, you head the opposite land, and now you know twice as much. On the back of your page or the next page of notes, it talks about endothermic. Endothermic reactions have to be supplied with energy. We have to put the energy in to keep the reaction going. The delta H has to be positive. The energy has to be a reactant. And in this case, you mix chemicals together and it gets very cold, like a chemical ice pack. It will involve bond breaking normally, and therefore decomposition normally. So our graph will look similar, yet different. Here's our potential energy. We still have a peak here, but we don't care about this massive peak, not until Chem 12, great fun. But what we see is the reactants have less energy than the products. So we have an arrow pointing up, delta H is positive. All those things indicate it's endothermic, and the energy being written on the reactant side indicates it's endothermic, guaranteed. So if we stop putting energy into our potassium chlorate, it will stop producing oxygen. The reaction just shuts down. So that's the difference between exothermic and endothermic. In the exothermic case, we have an arrow pointing down. That energy we can use to heat a home or power a car. In this case, this is energy that we have to put in, and we'd be doing other things. In this case, we're trying to generate oxygen. We stop supplying energy, we stop making the products. Hopefully that makes some sense.